For analyzing extended XAFS data, we use Feff calculations to simulate the XAFS scattering factors and then refine structural parameters such as near neighbor distance and coordination number to match experimental spectra. As a theoretical physics code, Feff is a pretty straightforward program to run to simulate XAFS, but using it well can still be one of the more daunting tasks for novices starting out with XAFS analysis. Hi, I'm Matt Newville, and this is part of the video series for using Larch for XAFS analysis. In this video, I'll show you how you can use XAS Viewer to set up and run Feff calculations for extended XAFS. I should be clear that while the Feff codes can be used to calculate XANEs and RICs and other X-ray core level spectroscopies, the versions of Feff that we have included with X-ray Larch are only able to do extended XAFS calculations. For modeling extended XAFS, we mainly think about the photoelectron ejected from the absorbing atom in the X-ray absorption process. This photoelectron will scatter from the neighboring atoms, and it is that photoelectron scattering and returning back to the absorbing atom that explains the XAFS oscillations. It is then most convenient to think about XAFS as a sum of paths through the molecule or crystal that the photoelectron can take from the absorbing atom and back as it scatters. That is, there would be a path from the absorbing atom to the first neighbor and back, and then a path from the absorbing atom to the second neighbor and back, and there may be paths from the first to one neighbor and then to another neighbor and then back home, the so-called multiple scattering paths, which can be important in some cases. All of these possible paths can contribute to the XAFS, though typically only a dozen or so of the paths will be significant for most experimental spectra. So with this sum of paths formulation, you could say that each individual path contributes separately, or you could group paths together of nearly the same distance into a shell of atoms. Say all 6 near neighbors in a rock salt structure can be considered one path with 6 identical paths. The XAFS from each of these paths will then depend on the neighbor distance, the coordination number, and some measure of distribution in those distances for that shell. But it will also depend on these non-trivial electron scattering factors that will depend on the species of the absorbing atom and on the scattering atom. And this gives XAFS, while this gives XAFS some sensitivity to Z of the scattering atom, it also means that we need to get those scattering factors somehow. And at this point in time, using Feff is the simplest and easiest way to get those factors. So the Feff program can simulate XAFS starting with an arbitrary cluster of atoms. You give it positions of atoms, and it tells you where the scattering paths are from a selected absorber and calculates all of the contributions, all of the paths and the contributions of those paths within the cluster. This is exactly what we want for modeling XAFS data, but the question then becomes, how do we get that cluster of atoms to simulate our structure, and how good does it need to be? One of the most convenient ways is to start with a crystal structure. You don't have to start with a crystal structure if you have a calculation from molecular dynamics or other simulation of where the atoms should be in a crystal or in a glass or a liquid or a molecular structure. That's fine. And for sure, XAFS does not need to be done on a crystal. But in fact, a crystal structure is a convenient place to start because we don't need the structures to be that accurate. We're simulating the local structure. And so many crystal structures can be found with pretty similar local structures to the kinds of systems we're analyzing. So the calculation should start with a cluster of atoms that's close, but doesn't need to be perfect. So a crystal structure is, in fact, a good way to start. So, and one of the reasons why a crystal structure is a good way to start is because a lot of crystal structures are available. So one way to get structures is to start with a crystal structure from the crystallographic information format, or CIF files. And in fact, there are a lot of CIF files available on the web that you can use to start generating the input cluster for the Feff calculation. In fact, in Larch, we include a set of about 9,000 CIF calculations from the American Mineralogical Crystal Structure Database. So we can start with that set of structures to stimulate XAFS. So to do that, from the XAS Viewer application, we can go to the Feff menu and say browse CIF structures, browse our crystallographic information format structures, and run Feff. Here this will bring up a dialog that's a search dialog for finding minerals by name. So as the example suggests, we could say HEMA and then say search for CIF files. So I should say that so here then are structures and a big pile of CIF files that look like this to encode the crystal structure for hematite. Actually, there's many hematite variants available. I'll talk about that in a little bit. But basically, they tell you where the atomic positions are for and the crystal structure to build the list of atomic positions. So from here, we could just click on Feff input text, and this down here will show us what the input structure it's calculated from that structure is. I'm going to back up a second and talk about the CIF database a little bit. Here we can browse by mineral name. So we could say ilm and get the ilmenite structures. You can also select by journal name or author name. So I'll say like Wyckoff. There's a lot of structures from Wyckoff there. I guess that didn't show up. You can also say that you require iron, titanium, and oxygen, and you want nothing else. Include only those elements. Search for CIFs. Again, those are only components that have, or only structures that have iron, titanium, and oxygen. And you can also select structures that have only full occupancy. That will lower this list as well. And there will be a lot of choices. They'll all be pretty similar in crystal structure. This database as it comes with Larch, has about 9,000 spectra. In fact, in your folder, in your home folder where Larch is built, and I'm going to show you this in just because it's actually important for things further down in today's video. Let me show you in the home folder, in your home folder, so on Windows that will be C and then your username typically. There's an X-Ray Larch folder. That's where the code has been installed. And there's also a Larch folder on Mac and Linux machines. This will be the .larch folder in your home folder. And in there is some information. Included in that is this AMS CIF full DB, which is 27 or so megabytes. That's been downloaded on this computer. When you start this, it will first start with a structures database that has about 9,000 spectra. It's about 9 megabytes. If it can reach our server millennia.cars.aps.anl.gov, it will try to download this CIF file with about 20,000 structures and use that. It's just more structures. If you can't download it, it's not a problem. Most of the structures that are in the smaller database are the ones you actually need for simulating XAFS data anyway. This one's just more complete from all of the structures at the American Mineralogical Structure Database. So let me show you. So for each of these CIF files, you can get the input file for Feff. You've selected the absorbing atom. You could change that to titanium. You could change it to oxygen. And then for some crystal structures, there will be more than one site for a particular atom. So you can also select which atomic site that is. I think if I go back to say, or if I say mag hemite, let's pick mag hemite and not include only those elements. Maybe something like this. Maybe one of these structures. There might be multiple sites for the iron atom, and you could simulate the XAFS for any of those sites at one time. You can set which edge you're using, the KL or M edges for Feff 8 version. Actually, with Larch, there are two versions of Feff, Feff 8 and Feff 6. I'll just assume that we're going to use Feff 8. It's the higher number. It's the better version, right? So whether it's really better is a separate question. that I won't go into in this video. You can also set the cluster size to use to do the calculation. So here, the CIF file here and the CIF text page encodes the crystal structure, where the atoms are in the unit cell. There's a 1D XRD pattern that can also be shown that'll come up in just a second. That's the expected crystal structure intensity, the 1D pattern for maghemite, and then the input file using this one atom as the absorber, and then it'll list that there's which edge to use for the absorber. I'll come back to this. And then basically the cluster of atoms. The atom that is currently at 0, 0 is the absorbing atom, but that's not encoded because it's at 0, 0, 0. It's encoded because it has this next tag of 0, which is the list of potentials. Basically, with Feff, you're telling it that there's an iron atom, some oxygen atoms, and then an iron atom that's not the absorbing atom, that doesn't have the core electron ripped out of the shell. And so it's really only thinking about 3 different atom types. So I think that's these potentials here that it calculates, those 3 different kinds. Now, to be clear, you could edit this file. You could move atoms around just by changing their XYZ coordinates. If you wanted to simulate a different element substituting for iron, say manganese, you could just change that to 25. And now the absorbing atom is manganese for this calculation. You can edit this file in other ways, which we might get to in later on. So let me just go back to making this start with the CIF file and then browse this. I think if I re-click on that, it'll reset what the structure is, and I'll hit run Feff. Then I'll run Feff for that. It gives out a bunch of messages as it's running, and then when it's done, it will show up the structures. I hope. It looks like it might have stopped running. In the Feff folder, there's this structure here, and these files have been, and I didn't want to do that. I don't know what that was. A bunch of, so now in our Larch Feff folder, there's iron 1, K, maghemite for this CIF file. In fact, when I ran this, you can adjust where these go, but it runs and puts the calculations in your Feff folder. And now, if we click on the Feff results, you will see a list of files, Feff1 for the closest neighboring atom, and so on. And there's a bunch of files for this because it's a complex structure. Let me go back to a simpler structure, say like just copper metal. I'll not include iron, and search for that. Now there's copper metal. Here is the crystal structure. It's got a lot of symmetries because it's a high symmetry crystal, and there's one copper atom at 0, 0. The 1D XRD pattern is pretty simple. The input file has some control parameters for how far out to calculate the XAFS and how far out to go, and it's copper. So I will just copper site 1, K edge, out to 6 angstroms. We're running Feff8, and we're going to hit run Feff. And we'll run that. And then again in our Feff folder, now it's encoded that there's the first shell has 2 legs, so that's a single scattering path. It goes from copper to a neighboring copper back to the absorbing copper. Here the brackets around the copper indicate that that's the absorbing atom. And then there's 6 atoms, 6 equivalent paths for the copper-copper at 3.6161 angstroms. You can also show the entire Feff input file that was used to run that calculation. That's read from this folder. So again, in your Larch Feff folder, there will be a set of calculations here. And we'll get to using these in a second. While we're here, I'm just going to run, because the first fitting example will be with iron oxide. So I'm going to search for woostite and pick something like this, or maybe one of the older ones. These are all pretty similar. And again, there's the 1D XRD pattern. The Feff input file has all of the header information in it that we need. Iron, oxygens at 6 oxygens at 2.15 angstroms or so, and then more irons at 3.04. So I should say that you can edit this file, you can change the titles and so on. We want to run the K edge for iron. We want S0 squared to be 1. As we'll see later on, we can use that as a parameter to the analysis, so we'll just leave it at 1 here. The control and print card should be left alone, but you can tell it how far out to go. We've told it to go out 6 angstroms. That's this number, our path of 6. And then SCF stands for self-consistent field. Feff 8, but not Feff 6, can use a self-consistent field to try to make the potentials more self-consistent in the calculation. It's been shown, especially by work by Bruce Ravel and others, including myself, that using self-consistent field for extended XAFS calculations just doesn't seem to be that important. It will add a lot of time to the calculation, so I won't do it here, but it seems that for some, it's still possible that it's important for very heavy elements, but for most cases, it doesn't seem to be important. Whereas for Zanes, it's critically important. If you're doing polarized extended XAFS, you can also include the polarization here. And the Feff documentation is actually pretty good for how to write this file and what to add to it. And again, you can edit this file before you run Feff. If you have, I should say at this point, I'll run this. While this is running, I will also say that if you have a structure, a CIF structure that's not from this database, you can read it in here. You can say file open CIF and read in a different CIF file, say from the open crystallography.net open CIF database, and run that as well. CIF files are notoriously complex and difficult to work with, so it's possible that you will find a CIF file that can't be converted to a Feff input file, but possibly that's fixable downstream or within the Feff input text. So you can try that out. And if you run into problems, that's a fine thing to bring up on the mailing list or to talk about. So again, here's a Feff calculation for Woostat, which is FeO in a rock salt structure, 6 oxygens in octahedral coordination and then 12 irons. And then further out, multiple scattering paths. So here in this list, it's encoded that the ones in black are single scattering, 3 are the triangular paths, and 4 are the four-legged paths that might indicate strong multiple scattering effects. So in a sense, that's really all there is to running Feff with XAS Viewer. You can browse through the large collection of CIF files that are included. If you want titanium and oxygen, if you're interested in doing titanium oxygen, include only those elements. You can search for CIFs, and there's quite a few. All the variations of TiO2 and Ti2O3 and other phases of the titanium oxides. Again, this won't have obviously molecular structures or protein or inorganic compounds, but will be useful for simulating lots of XAFS, especially in material science and geology. So I'm going to close this for now, because now that we've done some calculations, we can start to use them. And if we go over to our Feff fitting tab, we can then read in our Feff calculation. So from here, we will do this. This will help us do the sum of paths for the simulating the XAFS, and including fitting to data. But if we go to the Feff menu below browse CIF to run Feff, we can now browse our Feff calculations, and that will bring up this window that shows the 3 calculations that we did. Actually, they show them in order that we did them, so the most recent one is at the top. So if you come back weeks later and do a Feff calculation, that will show up at the top, and things from months ago will be at the bottom of the list. And again, we have these calculations that we can browse through, and now we can select some of them and import those paths. You could also click here and say select all above the current. I'm just going to bring in these 2 paths for now. And again, those are exactly from your Feff folder, so you can manage those with if you want to delete them, you can. You can also select all here and delete So you can say select all and then file. Oh no, it's select all and then right click to remove them. I won't remove any of them right now. But you can also just go into the folder and remove them, and then they won't show up on the list. So I'll import those paths. And when I do that, that flashed again. That's odd. Now we have a set of parameters that have been defined for each of the paths. We have two paths, one for iron to oxygen and one for iron to iron, and parameters to describe the XAFS. I'll talk about this in the following video. We can also, though, for each of these, plot our scattering factors, plot f of k and delta of k. So this is the magnitude and the phase shift for the iron-oxygen scattering. And if we do that for iron scattering, it will plot a new plot. But you can see this peak here for iron is peaked up at around 3 angstroms. And if I plot that for iron, it's peaked up more at 5 or 6 angstroms. That's an important effect in XAFS. And actually, the phase shift is also important. I'll talk about that in a little bit. Let me first, I can say plot this current model. It will apply these parameter values for S0 squared, E naught, and refinements to delta R for the R and sigma squared for each path. If I plot that path, there's the simulated XAFS for that in chi of R, and in chi of K, it plots that. You can click this to plot each path included. You can, if you give it a vertical offset, it'll plot those paths separately. So then you can say this is the sum of paths, and those are the contributions from each one, from each of the paths. And then these parameters have been applied. So you can adjust these parameters to increase sigma squared, and look at what the effect of that would be if I increase sigma squared for oxygen. Sigma squared for oxygen, I make that really big, then that contribution falls to almost nothing. And in R space, that will look like this. Don't plot those over. That will be the contribution with a huge sigma squared. If I make that sigma squared significantly smaller and plot that, the contribution from the oxygen and the iron would be about the same. So you can see that the sigma squared has a huge impact on what the intensity of that peak is. So I think that's what we can use for simulating XAFS for simulating real XAFS. We started with a structure from a CIF file. We showed how to browse CIF files from our database of 10 or 20,000 CIF structures. We ran Feff, and we imported the paths and displayed the contributions. So I think that's good for now. If you have any questions or suggestions, let me know in the comments below. And in the next video, we'll start with actually fitting and analyzing real spectra with these Feff calculations. Thanks.